Thank you, everyone, for joining the Accelerating Machine Learning with Vulkan webinar. During this webinar, members of the Vulkan Machine Learning Subgroup at Khronos will share the very latest updates to the Vulkan extension and ecosystem that directly benefit machine learning workflows. First, a couple of housekeeping items. If you have any questions during the presentations, please ask them using the Q&A feature located on your Zoom toolbar at the bottom of your screen. We are recording this webinar, and we'll share the link along with the slides when they are available. At the end of the session, please complete the short survey form to help us better design future events. With that, let's get the webinar started with Neil Trevett, President of the Khronos Group. Neil?
Hey everyone, I'm Neil. My day job is at NVIDIA, but I'm the president of the Khronos Group, and I'm very happy to welcome you all here today. We have a great lineup of speakers to talk about using Vulkan for machine learning acceleration. Jeff from Qualcomm, Pierre from NVIDIA, Leigh from Google, and the panel at the end of the session is going to be moderated by Kevin from ARM. And I'm going to start the session by just very briefly introducing Khronos and this new forum that we've established to give you some context before we dive into the technical details. So if you haven't met Khronos before, we are a non-profit open standards organization. We create open royalty-free API standards for 3D graphics, machine learning, compute acceleration, augmented and virtual reality. We have around 200 members spread around the world, everyone from large companies such as Google all the way down to single person startup companies, and everyone is welcome to join if they want a voice and a vote in how any of these standards that Khronos works on, how they evolve to meet the needs of developers. Khronos has a number of APIs that are used for compute acceleration and machine learning acceleration in particular. This is how they relate to each other in terms of their level of abstraction. We have the low-level APIs like Vulkan today, also OpenCL for heterogeneous compute. We also have some higher-level abstraction APIs such as SYCL, which is C++ programming with accelerator offload, and OpenVX, which is a graph-based vision and inferencing API. But here today, we are focused on Vulkan. The machine learning forum at Khronos is new. This is actually one of the first events that the forum is running. The basic idea behind the Khronos Machine Learning Forum is to create a place for the hardware and software communities using and implementing machine learning acceleration to communicate and coordinate and to better serve each other's needs. The forum is open and free for anyone to join. There's no fee, there's no NDA commitments, and no IP commitments. We will be establishing a dedicated meeting space online where we can share emails and documents and establish, we hope, an ongoing dialogue between anyone who's interested in acceleration for machine learning. The bottom line really from the forum is we want to have a good dialogue with the community so Khronos can produce better APIs sooner to accelerate the machine learning frameworks and applications that you want to develop and deploy. And I mentioned this was one of the first meetings. It's actually not the first meeting. We actually ran a summit meeting back in October, which was the precursor to the forum, where we had a number of the practitioners in the industry coming and presenting to Khronos how they were using our APIs, and in particular, the pain points and friction points that they were experiencing. That is really good feedback for the Khronos working groups. And we arranged a second follow-up meeting in January, where we were providing some feedback and some pointers on how some of those bottlenecks and friction points could be addressed. And it was, I think, a very valuable experience for everyone involved. Now, under the umbrella of the forum, we're beginning to arrange a series of webinars. This is the first, focus on Vulkan. For machine learning, we have an OpenCL oriented one coming up in May, and just a week or two's time. And we'll have more for SYCL, OpenVX, and other Khronos activities. And then we're planning to start the member-only meetings in July 2022. So this will be member-only meetings to have discussions on topics that are of interest to the members. So we hope that everyone here would like to join the forum. Please do, you'd be most welcome. And we're very interested to hear about what topics you would like the forum to start covering in its first few meetings. I've put the link there in the slide, and these slides will be posted. So all the information that you need to join the forum now is there on that webpage. So, and I've also had some resources here. So again, these slides will be posted. So with that, without no further ado, I'd like to hand over to Jeff from Qualcomm.
Thank you, Neil. So my name is Jeff Ledger. I am with Qualcomm's driver team. And today I'll be describing a proposed extension for accelerating ML workloads on the GPU. So the motivation for this extension, the motivation for the extension is really to have efficient dispatch of ML inferencing workloads. And it's aimed at either applications or frameworks that are already using Vulkan for computer graphics and want to augment those workloads with ML workloads in addition to the compute and graphics. And we want to make certain that the ML workload is efficiently executed on the GPU or whatever IP we're targeting. And that means, importantly, that in order to have efficient execution is optimal layouts and tuned kernels that are well optimized to the particular IREE you're running on. We also want to have easy and convenient interop between the different workloads, graphics workloads, compute workloads, and ML. And part of that efficient interop would be no copies of resources if resources are being shared between ML and graphics, no stalls. We want the client to be in charge of the command buffers that are being submitted to be able to control when those are submitted to the IP for execution. And be in charge of synchronization as well. Async dispatch so that the ML workloads can operate concurrently with other workloads. And the focus of our focus from Qualcomm is primarily accelerating ML on the GPU itself. However, this extension does also, if you had other IP cores, DSP or NSP, that is able to process ML workloads, then those workloads can be dispatched through this extension to those other IP cores. We also want to, where possible, we want to align the extension with DirectML to ease the portability between different APIs. So the principles that we sort of followed in designing this API was primarily with this API, we want to accelerate the ML operations themselves, and we use in DirectML that they use the term meta commands to refer to these basic ML primitives or ML operations. And by providing an API that allows you to accelerate these meta commands or ML operations, it creates basically a backend in Vulkan that the ML framework can target to efficiently execute the ML model. In this extension, each of the ML operations, we use a VK pipeline to represent those ML operations. And we record the ML dispatch or ML workloads directly into the Vulkan command buffer. In this extension, proposed extension, we have 16 commonly used ML operations that will be natively supported by the implementation. And I have those 16 proposed ops listed in the boxes to the right. It is possible to also create additional operations by expressing them directly in a compute shader, and I'll explain some details about how that works. For the 16 natively supported operations they have on the right, these would be provided by the IHVs in the form of basically hand-tuned compute shaders or kernels. And in our experience, the hand-tuned kernels can significantly outperform anything that you would be able to express in SPIR-V. For the actual definition of the ML operations themselves, the mathematics and the behaviors in this proposed extension, we rely on external definition, either NNEF or ONNX, to provide the actual definition of the ML operation. In the draft spec, we rely on NNEF definition of those operations. Some of the key features of the extension: we looked at trying to leverage either 3D resources or buffers. Our finding was that those resources really weren't well suited to represent a 4D, 5D tensor object that the ML operations operate on. And so in this extension, we propose adding in a new resource type into Vulkan, which is called the VK tensor. And when you create a VK tensor, it follows very much the same pattern as creating a VK image or VK buffer. We leverage the concept of tiling optimal to allow for efficient IHV specific layouts of the data in the tensor. We create a view object, a VK tensor view, which very much like a VK image view allows for hardware optimized descriptors of the resource and the view of the resource. The extension also adds in some utility functions like copies and barriers between the tensor operations. Where possible, and pretty much throughout this extension, we leverage fit into the existing API very closely. So for instance, although there is a new resource type, the VK tensor, the way that you create the tensors and the tensor views and the way that you allocate memory and how you bind the memory to those resources all follow the existing patterns in the Vulkan API. And similarly, the way that after you've created the pipelines for your ML operations, the way that you bind those pipelines to the command buffer and how you execute the pipelines and barriers between the pipeline objects and descriptors all follow the patterns that we have in the Vulkan API. So it fits in very nicely. The last bullet is sort of a detailed issue, a detailed point in that the individual ML operations, the ML pipelines can either express a single ML operation or a fused operation. And so I'm showing that we basically support two operations that can be fused together: that primary operation, which can be something like a convolution, and then a second operation, which can be an activation operation like a ReLU or a sigmoid. And so the extension supports this ability to combine two operations together into a single pipeline. And that allows for better efficiency on the GPU. So I mentioned that in addition to creating pipelines with an IHV optimized kernel, the extension also provides a mechanism where you can create your own custom ML operations by adding in load store operations into a regular compute shader or compute pipeline to perform an ML operation. And so this slide basically describes how that works. The extension adds a couple of new built-ins, both in the GLSL language and SPIR-V language, and we would also add something similar in HLSL. These built-ins allow you to perform a load operation and a store operation. So when you declare, in this example, you declare the input tensor and the output tensor using a new type, which is a tensor 4D or tensor 5D. Another detail is that when you declare the tensor, you declare the format of the tensor. This allows us to better optimize the hardware instructions and the layout of the tensor. And then the load and store ops follow a similar pattern of image load and image store. Basically, this illustrates how you would be able to read and write tensors from a compute shader. In terms of the actual creation of the tensors in this proposed extension, it follows very much the pattern of images and buffers. 2 new APIs for creating tensors and destroying tensors. At the time you create the tensor, you declare whether it's going to be a 4D or 5D tensor and the layout of the tensor. You specify the kind of tiling you want. In this proposed extension, we only support single component formats. So the actual VK format is always going to be a single component, and we have 2 required formats, and the other single component formats like R16 uint and such are optional. APIs for creating and destroying the view of the tensor. Getting the memory requirement for the tensor works very much the same as getting the memory requirements in Vulkan for an image or a buffer. The API works exactly the same. Binding the memory to the tensor works the same as binding memory to a VK image. And I did mention that we also added in a copy operation for copying between tensors. And so the bottom line here is that the APIs for tensor very much follow the existing APIs for other resource types in Vulkan. In terms of the actual ML pipelines, and again, the ML pipeline is a case where you are creating a pipeline object, and you're going to rely on the implementation to provide the actual highly optimized shader code for that pipeline. So for instance, you will create a pipeline and specify the pipeline is going to be a convolution pipeline, but you don't actually provide the compute shader code. The implementation provides that information. So we added a new API call, create ML pipelines, that creates 1 or more pipelines where each pipeline that's created typically implements a single operation. I did mention you can fuse 2 operations together, but generally it's going to be a single operation, like convolution or reshape operation. At the time you create the pipeline, the inputs are fully described, and I'll have a slide that goes into more detail on how that works. In addition to creating a pipeline that operates on tensors, there are use cases where you want to create an ML pipeline that actually reads from a VK image or VK buffer. And so for those use cases, we actually added in a mechanism into the extension where you can create an ML pipeline that reads from or writes to a VK image as if it were a VK tensor. And so the 2D VK image is treated as a 4D tensor where the n size is always 1, and the C size is equal to the component count of the VK format. So if it's like an RGBA format, then the component count will be 4 for that image treated as a tensor. There are a few different additions to the interfaces to the ML pipeline. And so the first thing is that some pipelines take what we call a static tensor input. And so for instance, for the convolution operation, the weight and bias are typically going to be constant across many invocations of that model. And so for those types of operations, we flag those inputs as being static tensor inputs. And I'll describe a little further on what static means. The other new thing about the pipelines is they also require, some of them require supplemental storage buffers. And so there is a scratch buffer, which is a buffer that is provided by the application so that the pipeline object can store transient data. And it's a constant buffer object as well that holds persistent data. And there is a new API called update ML constant buffer that this is where it gives the implementation an opportunity to read from static tensors and write those static values into the constant buffer. So in the case where tensors are relatively static, this mechanism provides an optimization for the implementation. And I also mentioned that there's an additional get memory requirements API call that gives you information about the size of the scratch buffer and size of the constant buffer required for a particular ML pipeline. This slide goes into some details on the creation structure. So I mentioned at the time you create an ML pipeline, you provide various information, one of which is the primitive ID. So this primitive ID is an enum that will identify, is this pipeline going to be performing, for instance, convolution or ReLU or PReLU and such. You also provide the at the time you create the pipeline, you provide the set and binding information for the constant buffer and the scratch buffer. And there is a supplemental structure, this prim create info, and this structure is unique for each primitive type. So for instance, the prim create info for a convolution is different from the prim create info for a prelude operation. And I'll go into some details of this on the next slide. So this slide shows, for example, what the primitive creation structure would be like for a ReLU operation, or actually a leaky ReLU operation. ReLU takes two tensors. It's an input tensor and an output tensor. And so for each of those, you provide this structure that describes the set and the binding for that tensor input, and links to an additional structure that provides the details of the tensor. For instance, the format of the tensor, the size of the tensor, how many, the size in each dimension, the strides. So the bottom line here is that at the time you create the ML pipeline, for each of the tensors, the implementation knows the format of the tensor and the size and shape of that tensor. And that allows the implementation to actually create a fully optimized ML kernel that is customized, specialized for that particular set of tensors that are being used for that ML operation. When you actually want to dispatch your ML operation, there is a new dispatch command that's added in. The dispatch doesn't take any actual parameters other than the command buffer where the dispatch is being recorded into. And when you issue this dispatch, it iterates over all the elements in the output tensor and computes them from the tensor inputs. And it'll read from whatever tensors, buffers, or images are needed in order to compute that output. And so this shows on the right what you would do in your command buffer. You basically bind the ML pipeline, and it's bound as if it was a compute as a compute kernel, and then you issue a dispatch. So, but typically you will bind the pipeline and then call a dispatch and do that over and over again. We also added in this extension an extension structure into the VK command pipeline barrier 2 API call, and that allows you to add in barrier ops on your tensor resources, similar to the way that you already can add in barriers on your image information. The overall status and the plan for this extension, we do have a full complete draft spec of the extension. It is available inside Khronos. It has not been shared externally. We, Qualcomm, have drafted this as a cross-vendor extension, so it's an EXT extension. We've collected various feedback from Khronos members and incorporated that feedback into the proposed extension. We have a beta implementation of this extension in our Arduino drivers, and really we are right now looking for or soliciting partner feedback to see what is the level of interest in this extension, what sort of feedback, what would people like to either for this to be supported or to be enhanced or what changed. I will mention that we also have a similar extension for OpenCL. That extension is shipping already today in Arduino drivers, and it will be discussed in a follow-up webinar on OpenCL. And so really we're looking for feedback from either framework owners or ISVs or IHVs on this proposed extension. So thank you for listening, and thank you for your time. And next up will be Pierre to talk about a different extension.
Thank you, Jeff. That was really good. Hi, everybody. I'm Pierre Boudier. I work at NVIDIA. I'm as well the chair of the Vulkan Machine Learning TSG, where we actually discussed Jeff's work and some of the work that I'm going to present as well. So I'm going to present an extension which is available on NVIDIA hardware, which has been available for multiple years on our recent hardware, which is called the Cooperative Matrix Multiply extension. Oh, so what is the goal and what are the motivation for that new functionality? So the goal is really to accelerate machine learning in general. So inferencing, obviously, training, any kind of workload which requires GPU acceleration. And when you observe recent algorithms, so for neural networks specifically, but for others as well, the critical operation is to accelerate large and low precision matrix multiplication. So in this extension, we expose FP16 and int8 data type. More could be added, but that's what we support today. And the problem is really that SIMT was never the right model for large matrix multiplication. And it was possible to do large matrix multiplication using compute shaders and just using this SIMT model. But in practice, shader also would decompose the algorithm into tiny mass operation, which would be dominated by trying to minimize read from memory, and so trying to write and read from shared memory, or to shuffle data between lanes. And the decomposition would be optimized for specific hardware platform and would not be, highly portable to other platform, including on the same vendor when you moved from one generation to another. So that is to expose a new abstraction, which is matching as well specific hardware unit that we have, that allows us to evolve the hardware unit. And it's really a subgroup-wide matrix multiplication. So instead of doing one mass operation per lane or supporting a 4 large matrix multiplication abstraction, then we expose a medium-sized matrix multiplication. And that's primitive, can be optimized by each hardware vendor, or can be optimized over multiple generation for one hardware vendor. So so the gist of it is all the invocations in a complete subgroup, so you cannot have partial subgroup, can cooperate to compute the result of that matrix multiplication, instead of having each lane computes one part of it and trying to summarize manually the output. The matrix is stored opacally, in that subgroup. So it's spread out, but you don't really know which lanes owns which part of the matrix. And just also can be a larger general matrix multiplication out of it for whatever purpose you need. So in terms of terminology, cooperative matrix is a new matrix type, where the storage and the computation is spread across the set of invocation. So how that's mapped is opaque. The only requirement is for that subgroup to be fully converged, so you can't have partial subgroups. The basic ALU operation in the building block of operation is a mass D equals A times B plus C, D, A, B, and C being matrices of different sizes. So we say that we do the format of those matrices is described at the high level as M and K. So the matrix A is really M by K size. The matrix B is K by N. So that when you do M by K multiplied by K by N, then you end up having a matrix of size M by N, which is the size of the matrices C and D, D being the result and C being the accumulator, the input for the accumulator. So which sizes are actually supported by the current implementation is queried by the VK extension. So those M and K and the formats are queried. So in our implementation today, we support 16 by 8 by 8, 16 by 8 by 16, and 16 by 16 by 16, and a few others as well. In terms of precision, we support for the A and B matrices FP16, so for the multiplication. And for the accumulator, C and D, we support either FP16 or FP32. So you can accumulate with the full precision, the 4 single precision or half precision. And obviously, the matrices C and D must always match. They can be of different type and size. We expose as well int 8 for the multiplying matrices A and B, and they would be accumulated using int 32. The integer being either signed or unsigned. So in terms of types which have been added to GLSL and SPIR-V, so for GLSL, we kind of like experimented with a parameterized type. So meaning that you have a basic type, which is f, cop, mat, nv, with a prefix for unsigned, signed, or floating point, u, I, f. And you specify as parameters number of bits, the scope, number of rows, number of columns, and that gives you a full family of types. In SPIR-V, there is a new type, and the parameters are added as person component type, person scope, person rows, person columns. All those parameters can be specialized constants, and the goal is to be able to write a few set of shaders or a single shader, but really to be able to specialize the shader for multiple hardware. So you don't want to write different instance for every configuration. So if the number of rows and columns supported by your implementation is different from another one, then you want to be able to reuse the same shader. There are very few constraints in GLSL and SPIR-V on combinations, but it's really the SPIR-V environment spec that describes what limits you. Some example, how you use those in GLSL, you define rows and columns as constants of 16 and 8. And now we have a matrix that we define with 16-bit precision, which is the entire subgroup scope, and size 16 by 8. That's your matrix floating point. And the same one in SPIR-V, you defined your variable alpha scope, rows and columns to be 16. Scope 3 is subgroup scope, then 16 and 8, which is the size of the matrix. Since those matrices are opaque, you need a new built-in to be able to load and to load into them and to store them out to memory. GLSL, we've created new built-ins with different either with a buffer as inputs, which can be full buffer or 16-bit buffer, and with an offset, which is a parameter element. Then you have a stride, so that if your data is not densely packed, then you can use a pack. You can use a stride, and you define if your matrix is column major or row major for input or output format. And you have similar functionality in SPIR-V. The difference being that instead of specifying a buffer and an offset from the start of the then you specify the pointer directly, which is completed by op access chain. All parameters must be equal across the whole scope. You can have different parameters for each lane, and all invocation in scope must be active. The building block for mass is matrix multiplication and add, and those are exposed using those new built-in function called mat, nor, add, nv, and the equivalent for integer, and same thing for SPIR-V op cooperative matrix, nor, add, nv. The dimensions of the type and types must form the MNK format that is supported by the extension. So you can specify anything you want in GLSL and SPIR-V, but they have to match what is supported. Otherwise, you're going to have error. The precision and the order of operation to actually do that matrix multiplication is implementation dependent. Different hardware vendor or different generation of the same vendor could be slightly different. So you could expect some differences in the least significant bits. And the return type for GLSL is derived from the type of C. Other operations which you can perform with those opaque matrices are component-wise arithmetic. So you can do plus, minus, multiply, divide, meaning that you can add, subtract, multiply, and divide two matrices, and that will just multiply each element of the matrix. So they have to be of the same size, obviously. In PRV, you have the equivalent add, negates, matrix time scalar, and divide. And I think I miss multiply somewhere. You can as well do some conversion, so construct a new matrix of the same size but using different component types. The cooperative matrices can be viewed as composite types, so it's as if you had a vector, but the number of elements of your vector is implementation dependent, and the mapping of that matrix is as well implementation dependent. You can still do some operation if you want to inspect those matrices. So you can query the lengths of the matrix in both GLS and PRV, and you can as well index within an invocation. So if you're on the thread lane I, you can say, give me the I elements of the matrix. You don't know where that element comes from. It could be from your local thread, or it could come from another thread with some shuffle operation. And you can extract those values to do element-wise tensor operation. And you can as well construct from scalar types. So the Vulkan extension on top of this PRV and GLS extension allows you to query the capability of the current device. As I said earlier, in the current implementation for FP16, for A, B, C, D type, we support the layout 16 by 16 by 16, 16 by 8 by 16, 16 by 8 by 8. And the C and D matrices can be either FP16 or accumulated in FP32. For unsigned 8, accumulator is 832, and the format of the, so it's layout of the matrices is 16 by 16 by 32, 16 by 8 by 32, and 8 by 8 by 32. And we can have the same one for signed integer. So in terms of performance, how does that work? So if you do a naive implementation in GLSL, then you can multiply one row by one column and output one value and get terrible performance because you actually have lots of redundant loads. So I'm not going to describe the actual GLSL code, but you can find it on a GitHub repo, which will be linked at the end. So if you just replace that code and do something, but with a cooperative matrix as a building block, then actually you get much better, but you're still very memory limited. You get about 8 times faster or 10 times faster than what just using a single float operation. So it's the single lane operation. So another way to improve is to use a building block which is called a tiled scalar multiplication. So instead of doing an entire lane, what you do is you take a small tile in a column, a small tile in a row, and you compute all multiplications, and you output a 8 by 8 tile in this example. And that gets better because you reduce the number of loads that you can do, and then you do more math with those loads. So you can do something with matrix multiplication. And so you can have, in this case, if you look at the column of cooperative matrix, it's 3 by 1. The row is 1 by 3, and then you create a bigger block of like 3 by 3 cooperative matrix in the outer loop, and then and it's not much more complex than what you would write for scalar, but you get a significant performance bump, about 10x again compared to the naive cooperative matrix multiplication that we had earlier. The next step to improve even further is instead of to load directly into memory the matrices, sorry, to load directly matrices, is to stage a copy from buffer to share and have all subgroups cooperate to load the data. There are multiple benefits out of that. You can overlap the buffer loads with matrix mass. And actually, because you cooperate, then you can actually reduce number of loads overall that you would do by sharing data in shared memory. So there are a couple of examples that we give here. So if you have FP16 and you split 8 subgroups, 8 subgroups can split 256 by 256 tile, and so you have 8 tiles of size 128 by 64. If the size of your of the K is then 32. So you can cooperate to copy so A block, so 256 by 32, and B block 32 by 256 into shared memory, and then each subgroup loads the portion it needs from shared memory, and then you do all the math. And so you reduce significantly the number of loads that you do for all the math that you're going to do to do multiplication. And give another example for 8-bit integer. The trick part with 8-bit integer is accumulator is int32, so it has a 2x performance penalty on register file compared to the prior example, so it hurts latency hiding. And as well, because we double the mass rate for integer, then it's harder to hide latency because we have twice as much mass. So we are much farther from the speed of light. And so the performance numbers, if you compare to the earlier numbers, then they're much better. And you get really high performance. The pseudocode, which doesn't fit on this page, is the following. So for you fetch A and B for tile K and for the tile offset K equals 0 into register file. Then you have a barrier because you have to wait for shared memory from the prior operation to finish. You copy tile K from the register file to shared memory. Barrier again. You fetch again A, B for tile K plus 1 to register file for the next iteration. And then you do mass loop and then you iterate. So the full source code is available on Jeff Borg's GitHub. What we've wrote initially, this is a presentation and the author of the extension. And you have all the source code there. And so you're free to download it, copy it, modify it, and have fun with it. And I think that's the end of my presentation. So let's move to Lei, who's going to talk about IREE.
Hello, can you hear me?
Sound good.
Thanks, Pierre. I'm Lei. I work in Google and leading the effort to pushing for Vulkan Spearway in MIR and IREE. So today I'm happy to talk about our experience of using Vulkan Spearway in IREE to build a standard and convolution-based ML stack. My talk is basically structured in 3 components. First, I'm going to talk about some of the challenges we witnessed that existing ML stack faces, and why we believe Vulkan Spearway is a good base solution towards addressing them. Then I'll talk about IREE's architecture in a high level, with some focus on Vulkan Spearway related components. Lastly, I will show some performance numbers with the current Vulkan status and show what's upcoming as a roadmap and the tasks. So diving into the first part about challenges and what we believe why Vulkan is a good approach to address them. So in recent years, basically we see great advances in ML. Various folks are interested in different components and they are pushing for more and more choices at different layers. This is great for the choices, but it also brings lots of challenges given the huge problem space we are facing there. we are seeing a combinatorial complexity due to a bunch of factors. First, the trending ML model architecture keeps changing from initially planned deep neural networks to convolutional neural networks, and then recently transformers and MOEs and whatever in the future. The user interest in the leading frameworks is also keep shifting. So that's like the programming side. On the execution side, there is a growing like landscape of heterogeneous hardware. Existing chips basically picking on more specialized functionalities for vector matrix processing. And there is a large amount of like new accelerators dedicated for AI and ML workloads. For inference and deployment specifically, there are lots of scenarios it needs to capture. So we have a huge problem space here. Existing ML stacks didn't anticipate this at the beginning for sure. So they have design choices basically a bit overfit to the previous situations. One of the key issue there is basically the ad hoc in-house hardware interfaces. By that, I mean basically where we go from machine agonistics to machine specific. So in previous situations, we pretty much only need to handle one or two architecture. It makes sense to basically define the interface at a high level, like ML graph or op level, where we can devote extensive manual effort trying to write a set of kernels for each of the architecture we keep. But this is quite challenging. But this is becoming challenging with now more and more hardwares coming into existence and more heterogeneous situations. So for a new hardware to integrate, basically it needs to build up a full AI API runtime kernel compiler story. That is fine for existing hardwares which have already built out, but it's very costly and time effort consuming for newcomers. On the other side, it also means stack needs to have a full story for hardware and the deployment scenarios. So also very challenging. So what do we see in the situations that we have fragmented solutions basically, having each solution specialized towards a subset and often lack adaptability and generality. There are extensive duplicated manual engineering efforts within or across various stacks. Interesting thing is that if we look closely, these challenges aren't specific to ML. We actually see similar things happened in graphics side. So in graphics, we also have a domain-specific way of programming many different hardware, many different GPUs on different form factors. There are similar challenges there. Actually, we can draw some parallel there. For example, the rendering technologies and the pipeline are akin to ML model architectures, and then game engines are like frameworks. So game engine also needs to handle various GPU architectures for different form factors, and arguably game engines are facing even more challenging situations with all those like ad hoc other stuff, multiple resources struggle with and stuff. But in general, game engines scale and can customize better. That is one of the key missing characteristics in ML stack. So how to address these challenges and interact with hardware at what layer is actually a pretty well explored and developed area in graphics. We believe that ML stack can tap into this to be generalizable too. Basically, there are two key points. One is that we need a formal standard to bridge ML stack with the hardware. Like you can have many game engines per your needs. Each of that don't need to build up the full solution for like hardware support and deployment solution. It just need to plug in the standards to pick up support for various hardware. On the other hand, implementing the standard would support a various stack for a new hardware. The standard should be supporting both commonality and optionality, which are both important. Another point we have learned basically is offline compilers are a good way to automate the conversion flow from high-level programming model down to execution machines and share lots of functionality between different architectures, share the complexity away from the runtime driver, and eliminate support differences among different basically implementations. Together, these two should address many of the ML inference challenges and help build an inclusive, generalizable, and performance stack. Vulkan SPIRV is just like the latest incarnation of this standard compilation-based approach. So they represents years or decades of learnings and presents a modern, clean-based solution towards ML stack 2. Basically, they explicitly expose hardware functionality, not very opinionated with high-level structs like previous generations of APIs. This is good for basically developing whatever higher-level use cases without getting blocked by the hardware, by the API, and they are low-level enough, suitable for auto generation. This is both for the device executable side and also host scheduling side, which is actually a key factor for a key differentiator for IREE. And obviously, they are readily available on many platforms, meeting various deployment needs. So we don't need to plumb through the whole stack involving developers, platform holders, hardware vendors, again, for ML. So this is basically the challenges and why we choose Vulkan SPIRV as a standard compilation-based approach towards addressing them. Next, I'm gonna talk about what is IREE and the general architecture of IREE. IREE, in a sense, is IREE briefly is a end-to-end compiler and a runtime. It is based on MR, leveraging MR's ability to define multi-level abstractions and then doing conversions between them. It is also an early adapter of MIR and actually co-develop with MIR. In IREE, we have this unified IR that handles both host scheduling and the device execution. The aim is to scale up to data center and down to mobile and edge deployment situations. So to achieve that goal, it requires IREE to have a few key characteristics. First, it must be standard community-based. There is no way that we can actually build up this whole scope by ourselves. So we basically aggressively adopt standards and being open as much as possible, working with OSS community and other interested parties. All our discussions and develop is open, which anybody can feel free to join and discuss stuff. IREE is very compilation based, that we use compilers as much as possible to automate various tasks. This includes the traditional kernel code generation part and also the task scheduling on the host side, which is one of the key differentiator of IREE. We want to basically codify some of the best practices of writing scheduling in compilers with this approach. With MR's power, we can actually have one unified IR to represent them together. This allows some very powerful whole program optimization. A trivial example is that we can extract like some of the fail buffer as either wiki command fail buffer or generating kernels for it. Yeah, the goal is to be being scalable. That means like considering also like challenges from different deployment scenarios. For data centers, typically okay-ish to assume that the task is the only running job and taking ownership of the full resources there. But for like scenarios like mobile and edge the app is typically running in an environment that lots of apps are interleaving and competing for resources. So we need to be aware of resource constraints and being cooperative with other Twitter users and scenarios, basically. So with that said, basically diving into a little bit of IREE's overall architecture. So this is the end-to-end flow envisioned by IREE. IREE, of course, does not provide them all. Lots of like components are from the ecosystem. So from the top left, we have like a bunch of importers for different frameworks and runtimes. Right now, we have fairly good support for TensorFlow and TF-Lite. JAX is being plugged in right now, and the PyTorch development while TorchMR is going very well. And there is also Onyx runtime, or Onyx format basically planned. After importing, the initial model will be represented in MLR form, entering MLR ecosystem. Then we give that to the core IREE compiler, which first goes through the flow stage, which is for the core task there is for compute workload partitioning. In the original model, there is no differentiation, just a bunch of like high-level operations containing convolution, MATMO, element-wise ops, and a bunch other stuff. Flow looks at the graph and identify the dense computation ops, routing with convolution or MATMO, and move that into dispatch regions, including all the associated that can be fused component like element-wise operations. Then after flow, we go through the stream conversion step. The main task there is for async scheduling. Basically, flow gives flow tracks various like dispatch regions as a bunch of like as a DAG, and then the stream is purpose basically to have a more streamlined scheduling of the task using previously used depth chains from compilers, convert that into like tokens, effectively map into timeline semaphores under the hood. So after stream, we have a partitioned graph containing host and device logic, and we have a scheduled execution scheme basically. And then the next step is haul, which materialize the partitioning and scheduling, and by generating ABIs and by generating ABIs between the host and the device side. And all the management of the buffer will also be concretized. Buffers are exposed now with descriptors, and descriptors has like how Vulkan manages resources. So then after haul, we have this fork between the host and the device code generation. Device code generation side, there is nothing too surprising. It's just like traditional code generation, which you can go either, depending on the target, you can go either to LVM to generate various CPU architectures, or BTX for CUDA, ROCm for AMD GPUs. And also you can go to SPIRV to target Vulkan, Metal, or Web GPU. Then what's interesting is on the host side, which you have the option to generate VM ops. VM ops is just like the virtual instruction set for a IREE virtual machine, minimal IREE virtual machine. VM ops basically only contains, is very constrained, only contains stuff like resource management and basic math ops for computing shapes and synchronization. And if VM is not an option, it's like too heavy probably, then there is an option to generate C code directly for the host side that you can compile the generated C code into your like application directly without having the effort to like plumbing into a VM. And then there is also the option to generate LVM code to directly generate certain CPU architecture instructions. So if going down to the VM approach, we generate a IREE module, which is a flat buffer format that contains both the host scheduling and the device kernels. That is VM bytecode or some static share library for CPU or SPIR-V for GPU. This module can be run with the IREE runtime, which contains the VM for interpreting the VM bytecode and a proper whole implementation, either mapping to CPU or Vulkan or CUDA, ROCm, or web GPU stuff. So from the graph, I think it's relatively clear that the whole system is strongly layered. There is lots of optionality here, and they're allowing you to choose basically depending on your needs. What we are building with the IREE is essentially just a toolbox. We try to provide many choices and try to match various needs. There is no one solution for all, and we don't demand that. And it's up to the integrator and the user to decide which component to choose. Okay, this is basically the core compilation flow explained again, but more from MIR's perspective, talking about dialects and how they are converted between each other. So I won't repeat because I have explained most of the stuff in the previous slides. Just want to call out a few interesting parts that first, I think it again shows about layering. We are basically trying to build the right abstractions at the right level and chain them together for better structure and ease of development, not like how a monolithic stack that involves everything and it's super hard to modify or add new things without breaking others. Another aspect I want to highlight is that the amount of reuse. Input conversion is basically leveraging existing converters from the MIR ecosystem. So any framework model representation, if there is a way to plug that into MIR, convert that into MIR, it is just like mechanical work to get plugged into IREE. So on codegen side, we reuse linear vector level conversions in MIR code and only fork at the very last step. So there is also a great amount of reuse there. Compared to existing ML stacks duplication and manual work, this should be good improvements. Now focusing on the IREE runtime side a bit. IREE does not have a traditional fat runtime like existing frameworks that bundles everything. In an existing framework runtime, you can typically see stuff like significant context, and there is knowledge of high-level operations for convolutions, multiple stuff like that, and model runtime optimizations, fed kernel for all these high-level operations for different architectures, and maybe several thread pools and scheduling logic, and redundant error checking. All this is bundled together. It's not easy to extract components. They are sort of like a one-for-all solution. On the IREE side, as discussed before, we tried aggressively to do offline compilation as much as possible, that we generate VM bytecode for the whole site and generate native code for different ISAs if possible, or go as much lower level as possible. The application takes in the VM bytecode. It has the option to also use the IREE VM interpreter, or it can, as said, use C code generation to directly embed the logic inside the application. The whole library is also configurable depending on what you want to target. And the VM is written in the most efficient way, trying to satisfy constrained environment like mobile. So on the runtime side, I have another thing I want to further expand a little bit on. It's about the whole. It is actually very interesting that it is basically entirely inspired by Vulkan. So we observed tiled-based architecture are quite common nowadays, including GPU, CPU, and even some actuators. They all have this multiple level of memory or compute hierarchies meant for compute in tiled fashion. So we want this one whole for generalization to handle multiple architectures. It needs to do resource tracking, perform dispatching, and synchronization. It also needs to build pipelines to exploit this schedule hierarchy. For this kind of architecture, Vulkan's compute subset really provides a nice solution. So we think there is no need to reinvent the wheel. So we would basically borrow the idea there to use the API surface to build submissions, command buffer dispatches, and the code inside is basically doing workgroup, subgroup, instruction level tiling and targeting. This is an example showing the whole IR. There is no need to read into all the details. Some of the highlight part is what is interesting. From it, you can see it's basically effectively exposing the Vulkan C API as compiler IRs for automatic transformation. You'll find familiar names like whole, command buffer create, whole, command buffer begin, disk set management, dispatch, barrier, end. So this allows basically to use compiler techniques to optimize the runtime side, the API call side to like, for example, split, merge command buffers and doing barrier execution, barrier eliding, also things that are best practice for writing, sometimes are best practice for writing efficient runtime code. And there is also, it also shows the separation between the executables and the scheduling. Okay, that concludes the overall discussion of IREE architecture. Next, I'm gonna show the current status of Vulkan and some of the roadmap we have ahead. The general approach we have been approaching this is basically we are investing in basics to establish solid foundation for generalization and performance, because this is building an entirely new compiler stack that is gonna take time. It's not gonna be done in a year or something. So we want to make a solid foundation. Tasks benefiting a broad range of models and architectures are prioritized. The goal is to provide a reasonably good default solution towards all cases, but recently leave the door open for power users to hyper-tune specific cases that they care about. Thus far, we basically build out SPIR-V code generation in MIR and the Vulkan runtime in IREE. We can correctly compile and execute many vision and language models on various hardware. It can target Vulkan. We directly target Vulkan computers and use called Vulkan Compute API size subset. We are adopting like extensions proposed by Vulkan ML group, but for now, this is like showing the results using Vulkan Compute API subset. Optimization side, we are also focusing on. We are still focusing on widely applicable compilation optimizations. There is no manual automated tuning thus far. We just use one single set of heuristics and default parameters for basically everything. Given that transformers is basically taking over the world nowadays, we show a few transformer-based models on various GPU architectures across different deployment scenarios to demonstrate the generosity and also performance. We use mobile bird on mobile and mini LM on other deployment scenarios. Mini LM is a transformer distilled model, which is smaller scaled model. Mobile side, we use Pixel 6 and which has like roughly 2 teraflops computation. From it, basically we can achieve on-par performance with the TF-Lite OpenCL. And on laptop side, we choose Apple, which right now is going about Molten VK, doing the transformation layer. But still, even with that, we can beat TF-Lite Metal, which uses like Apple hand-tuned performance kernels, I believe. And in the future, we plan to implement a proper metal hole, but still reuse SPIR cogeneration. There should be even more space to improve the performance. This tool should be good to demonstrate the performance, given they are basically all on relatively constrained environments. And then for desktop and server, we haven't been focusing on that too much. So I didn't have time to get a comparison. But looking at the flop numbers, you can see basically the latency drops proportionally according to that. It should be a good demonstration of the generality across different deployment GPU architectures. We aim to, these transformer models are smaller scoped ones. They are typically challenging to get in good performance, given that because like larger scaled can fill the GPU relatively easily. It's like the smaller scaled one challenging. And the end goal for us is actually to support for pipelines like ASRs, and that is still under development. On the mobile side, which is also even more demanding, and their vision models still have a stronghold. We also show 3 vision models on Pixel 6 to demonstrate the performance and how much close we are and how much work is left to further close the gap. Compared to transformers that we have nicely shaped matmos, vision models are much more challenging for compilers to get performance nicely, because all the convolutions has basically strange shapes and would require various levels of padding and stuff. I show a decomposition of TF-Lite latency on buffer versus texture. By default, TF-Lite uses texture because it has far superior support for cases and avoids all the padding overhead and such. So look at the buffer performance. In IREE, we don't support textures yet. We solely use buffer for now. Looking at the buffer performance, basically, in IREE, we can achieve on-par performance with the TF-Lite. With texture, there are still some gaps to close. What is interesting is that even with the buffers, we can basically meet the performance of texture of TF-Lite and texture for mobile BERT. So with that said, it's clear there are lots of things and tasks we need to do in the future. This is a roadmap. There are general functionality features we need to implement, like smaller bit widths, and also the runtime. The initialization overhead is large right now. We need to reduce that. We haven't really paid much attention to it yet because we want to get latency in place first. And then there are general optimizations like better fusion. And as the vision models showed, better buffer layout supporting texture is not something we need to do. And there are general applicable techniques like search and auto-tuning can also help. This approach, extending a little bit beyond Vulkan, we can also reuse the SPIR coding and together with web GPU hole to target web platforms and the metal hole to target Apple platforms. That is all I have for today. There are some references here. Please feel free to take a look, and also please feel free to join our mail list or chat room to discuss further.
Thank you, Lei. That was very informative. Next up is the Q&A portion of the webinar. If you have questions, please submit them now using the Q&A button in the toolbar at the bottom of your screen. Our moderator for the Q&A session is Petit from ARM. Kevin?
Hello. So we already have a number of questions that panelists have been eagerly providing initial answers for. We still have one open question from Adam saying, this sounds great. Do you have any performance comparisons with JAX on SPIR-V versus PTX? I guess that one is for Lei.
Yeah, I don't have that right now because like JAX support is still being plumbed through. So we haven't reached the stage trying to benchmark some whole models across different backends.
Okay, thank you, Lei. That's one of them. Another one from May. For IREE, do you see computation time issues? Is table gen slow?
I mean, the whole IREE, we try to, because like the whole stack involves TensorFlow, involves MR, involves LVM, and the IREE stuff is certainly slow. I don't think TableGen is particularly problematic. The way we try to curb down the compilation time is trying to isolate different components, which also comes back to the layering and isolation concerns. For example, the importers are compiled into their own binaries. We don't always compile them together with the core IREE systems. And by doing that, basically we avoid paying the cost of always compiling TensorFlow, for example. So also like avoids all sorts of like breakages and here and there. Though like, I mean, compiling LVM and MR is costly. That is hard to avoid.
Thank you. I'll take a follow on that one. How much have you explored the trade-offs between performance and compilation time?
You mean compilation time at what stage? On device or?
Yes, I was thinking of a general trade-off also versus performance and compilation time. Presumably, the more time you spend compiling, and the better performance you can get in the end when executing a network.
I think lots of the stuff already done. I mean, we favor doing offline compilation as much as possible. We generate basically ISA level instructions for GPU side because SPIR-V is still like a little bit higher level. That's not possible, but hardware side, we just need to do last mile compilation of the driver, and so there should be minimal amount of actual compilation on the device. So for the compilation of IREE itself, the offline compiler, right now we haven't been spending too much time trying to optimize it aggressively. The focus right now is still trying to get basic infrastructures and basic optimizations in place, trying to improve latency. Right now, there are also, but still there are periodical runs like improvements over compilation time itself. Once we identify something being extremely slow, we basically look at the flame graph and see what's problematic and trying to cover that down. It's not like very systematic although.
That makes sense. Thank you very much. I think I'd like to go back to some of the questions that have been answered that I think warrant a bit more discussions. So there's one from LSC. The Vulkan computer basically is 8-bit integer supported with Vulkan compute shaders, and Pierre provided an initial answer saying that yes, it's a feature supported in Vulkan, and there's also support in the cooperative matrix extension. Do you want to expand on that?
Yeah, sure. So first of all, there are 8-bit integer and 16-bit integer capabilities exposed in Vulkan, and whether you can access them depends on the actual underlying hardware implementation and the implementation exposing it. So you can do regular math using those smaller types. On top of that, if you want to do full matrix multiplication using, for instance, for quantized neural network, then you need to have the cooperative matrix extension that does support as well as native type. So on NVIDIA hardware, we do support both FP16 and uint8 or int8 formats on all the hardware that supports extension today.
Thank you.
I will add to that on the Qualcomm proposed extension. We allow implementations to support ML primitives with 8-bit formats. Currently, the 8-bit is not required. It's optional. Each IHV can opt into supporting 8-bit formats. Only the FP60 and FP32 are required.
Thank you. I think still on lower precision integer types, it's probably worth mentioning that Khronos recently released alongside Vulkan 1.3 support for dot product operations also on smaller integers.
Yeah, I was going to mention that. So we have the new extension that does support a lower precision, 8-bit precision integer dot product. And for example, we would expect a stack like IREE that would actually take advantage of that instruction to implement some of the math.
Yeah,
Thanks.
supporting
In
that
case
is
people,
certainly on our roadmap.
great. All right, moving on. There's a question around the ML primitive extension. Can the pipeline take a subgraph supporting a limited set of operator does not provide sufficient coverage for many models? Compilation stage can be added to compile the subgraph similar to shader stage. So Jeff provided an initial answer saying that the extension as it is today doesn't support it, but they're thinking about it. Do you want to expand on that, Jeff?
I'm not really prepared to, but what I will say is that, we definitely recognize that there are cases where if you compile the entire subgraph, you can have a more efficient implementation of that than implementing a sequence of individual operators. So it is something we're thinking about. We don't really have anything to share at this point about that alternative proposed. It would be a completely different extension. It would be definitely different from the proposed extension I described today.
Thank you. Does anyone else wants to add something? Maybe Lei has got some input on that one. In your experience,
sorry, I have some feedback on that. So there are multiple ways you can take advantage of subgraph. One is to have better synchronization. The other one is to have better merging and cross layer optimizations. And so there are multiple ways that could be improved. And so we are, so some of those concepts have been discussed in the MLTSG as well, even beyond, in parallel to the Qualcomm extension that could take some subgraph or not. I don't know, but that we do recognize our opportunities there.
So on our side, basically we rely on aggressive fusion and stuff to form the subgraph. And there is also another angle that, for example, we can use secondary COM buffers for these subgraphs and then lower the overhead or constructing stuff.
In your experience, how much graph level optimization or subgraph level optimization provided in terms of performance boost versus just plain layer-wise evaluation?
We don't actually, it's like we basically look at the whole model like as a whole and try to identify what is the dense operations and then trying to form the display region by pulling in whatever that can be pulled into. It's an ongoing effort. And right now it's basically you have the dense operations and advanced operations following that. And there are also cases that you can have two totally unrelated operations pulling into together to share the same same dispatch. That is like more like the horizontal approach, versus like the fusion that takes elements of, which is the vertical approach. Those are both helps. It's hard to like as a goal, as totally see whether the thing is totally helps or not. It depends on the particular model architecture and also hardware architecture. It's it's relatively case by case. There are also cost model involved in this, I guess.
Yeah, thank you. We've got actually a comment from May in the Q&A section saying, we use TVM SPIR-V and graph optimization is very significant for performance improvements. So I guess that's another confirmation that graph level optimizations are very interesting.
Yeah, they are certainly very important. I mean, it's like smaller case by case and how you fuse them. There are certain things you certainly want to do for sure.
Okay, going back to some of the other questions, there's one I wanted to go back to. So Nihui was asking, saying that they've used the Vulkan Cooperative matrix in NCNN and got very significant performance speed up, and was asking whether other GPU vendors would implement the extension in the future. So I think I can take maybe an initial answer for that one, saying that ARM has been looking at this and doing some work to standardize the extension that NVIDIA have provided. What we've been looking at is a set of very small changes to make it easier to target on other hardware and use in slightly different contexts as well as a way of porting the SPIR-V extension to OpenCL. So I guess we'll see that appear in the coming months, hopefully. Don't want to give a timeline. Do others want to add a bit more on that?
Yeah, there was a second part of that question, which is about the BF16 data type. That format is supported on recent NVIDIA GPU, and we will look at. It's definitely something we are considering as a follow-up. I mean, it's not going to be a follow-up extension. Actually, we need to define the format, so we may need a follow-up extension to expose it, because there's no BF16 format in Vulkan. That being said, that's not specifically Vulkan related, but for machine learning in general, one interesting bit is BF16 is great for training, and for inferencing, FP16 is slightly better. That's something to be aware of. Because BF16 is great because when you do a training, you have small gradients, so you have very small values. So the extended precision around 0 for BF16 is great. When you do inferencing, you don't have those small gradients, so FP16 in general can work well. I mean, it doesn't mean that you cannot run into issues if you just swap them, but it's just a slightly different behavior between inferencing and training there.
A lot of people praise BF16 for the advantage in getting faster convergence while training.
Yeah, it is. Yeah, it's mostly because if you just use FP16, you naively, without doing gradient scaling, you may just get lots of 0 gradients, because your small values will just be changed to 0 instead of being small. So the way around that is to pre-multiply your gradient by a big value, and then you get non-zero gradients. And when you do the updates, you just scale back. So just a small trick that is available in frameworks nowadays. But it's a little bit more work just to get to work.
Thank you. Since we're talking about additional data types, recent NVIDIA GPUs also support other data types beyond bfloat16. Are you thinking of exposing these as well?
We are considering it for other data types. Especially the 4-bit ones. I think that's what you have in mind.
Or TF32
maybe. Oh, yeah, sorry. So yeah, we are considering it as well. The 4-bit is another The TF32 is one. Oh, TF23 or 32. That's one, and the second one is the 4-bit integer. Those have different use case. One is great for just not changing anything and getting better performance without changing anything from your 32-bit type that you typically have. So it improves programmer productivity, but it doesn't have the peak performance because your data is still 32-bit. It's you still have more data movement than if you were to convert to 16-bit types. And the 4-bit type has the highest performance, smaller footprint, but it is sometimes a bit of a research project to move existing neural nets to that. A lot of papers are showing that you can get away with very few bits, but most papers are written with more bits, so it just it's more involved to actually do that.
Thank you. I have a few more actually. EML primitives extension surely is likely to elicit a lot of feedback and comments. Where people could go to provide that feedback to Qualcomm and others?
Well, certainly my email address was in my slide deck. If you have any feedback on the extension, we'd be happy to collect that feedback and respond to that. If you're interested in details about the actual extension itself and you want more details, then again, you can, if you're a Khronos member, reach out to Khronos. You should have access to that extension proposal. If you're not a Khronos member, you can reach out to myself or anyone else in Khronos to ask for access, and we haven't released it publicly, but we could certainly discuss that and consider that.
Thank you. Another one, when looking at the IREE presentation, you showed performance numbers for specific devices. And any reason you chose those devices?
Actually, not a particular reason. So the idea is to show a bunch of different hardwares. I just grab the ones that are readily accessible to my side. So I believe basically any hardware will do. Some of the hardware we might not having the placeholder performance parameters yet, but it's relatively easy because we use the same heuristics right now in the compiler to target everything. The door is open for more powerful users to hyper-tune specific cases.
Thank you. And a follow-up on that one, are there any plans of adding more support for balancing across multiple devices or heterogeneous cases, say, partitioning the execution of a network between CPUs and GPUs?
Right, totally. That's one of the many things we have planned, and you see various placeholders in the whole stack, but not really fully developed yet. For example, the way we try to do dispatch region early and then have all the different architectures following and co-generating for the same dispatch region allows us to swap kernels for different architectures on the fly at runtime. So for example, we can detect the system overload and then decide to either invoke the kernel on GPU or on CPU or somewhere else. This is one other thing because the IREE flag buffer, the final IREE module flag buffer is containing all sorts things as a flag binary format. And also at the stream level, we have planned for basically device placement, device affinity and stuff like that. It's just right now, because of priorities and limited resources, we haven't really focused on those parts.
Thank you. Another one may be a more generic. If I'm an attendee and I'm wondering what the next event is and how can I engage with Khronos? What do we have in the pipe for that?
You mean just for machine learning in general?
For machine learning or machine learning on Vulkan?
Yeah, I mean, yeah, no, thank you for bringing that up, Kevin. So also, and there were some folks that missed the beginning. The machine learning forum, I think, is an obvious place to go. The machine learning forum, I think, will be a good group inside Khronos to help us organize this kind of public webinar, and hopefully people have found today useful, and it's great to see all these questions coming in. It is awesome. But the machine learning forum is also an opportunity for anyone outside Khronos to go deeper. If you want to, everyone is welcome to sign up for the machine learning forum. It's free. There's no IP commitments, so everyone can hopefully join, and that it'll give us more bandwidth and more time, to do deeper dives in some subjects that are interesting to the community, and it'll give us the opportunity as well to have an ongoing discussion on those topics as the Khronos APIs evolve. We want to use the forum to get feedback and to inform the community, so we can all work cooperatively together to move the whole field forward for machine learning acceleration. So yeah, anyone on the call, if you're not already a Khronos member, or actually if you are a Khronos member, join the forum. And if you're not a Khronos member, please do consider joining the forum. You would be very welcome.
Thank you, Neil. I think we're slowly reaching the end of the allotted time slot, and we no longer have any outstanding questions. Any final words from any of the panelists?
Thank you to all the speakers, and thank you to everyone for attending.
Yes.
Yeah.
Thank you to all our presenters and panelists today. We appreciate your time and effort, truly. As a reminder, a recording of this presentation along with the slides will be available on the Khronos Group website, and a direct link will be sent to you in a follow-up email. As you leave the webinar, please take a moment to fill out the survey that pops up. Your feedback is very important to us, and it helps us improve these presentations. Please let us know if there are any other Khronos-related topics you may be interested in. And thank you for joining us. We hope you enjoyed the webinar, and have a great day.